Today, we are going to go through a Gauteng province provincial examination, June 2024, grade 10, physical sciences. So we scroll down there. Its duration 2 hours and total marks of 100 there. Then we've got our instructions there and all the second page. Then we move on to the questions. So question number 1 there is multiple choice questions, and it says various options are provided as possible answers to the following questions. Each question has only one correct answer. So there is only one correct answer. Choose the answer and write only the letter A to D next to the question 1.1 to 1.10 in the answer box, e.g. 1.1.1e there, right? So we're going to start with question 1.1. It reads, for which one of the quantities given below is the correct unit of measurement? So we're looking at the units of measurements. So the first option that is actually given is current. So as we know, current is measured in amps. So current is measured in amps. So it means our first option there for current is wrong. Okay. Then the second option there, it says energy, the unit of energy should be in joules, so which is our joules, like that. Then C says potential difference, which is in volts. So option C there is the correct answer, that says volts. Then D, resistance, we know our resistance is measured in ohms, like that. So the correct answer is going to be option C, which is our potential difference. Then we move on to question 2, 1.2, which reads, a battery is marked 12 volts. Which one of the following is the correct meaning of 12 volts? So 12 volts, it says here, this means that 12 charges pass the battery. 12 charges pass the battery. This is wrong because there are not 12 charges that are actually going to pass the battery. Then it says here, this means that the 12 joules of electrical work is done per coulomb of charge. So this is our correct answer, which reads, this means that the 12 joules of electrical work is done per coulomb of charge. Then 12 volts again there. Regarding the 12 volts, option C reads, this means that 12 coulomb of charges pass through the battery each second, which is also wrong. Then D, this means that 12 joules of electrical energy is converted to light and heat. This is also wrong. Then we move on to question 1.3, which reads, in a small electrical appliance, a charge of 3 coulombs. So we're given a charge of 3 coulombs flows through a light bulb with a resistance of 6 ohms, and then in 12 seconds. So we're given the resistance and the time. Then it says, which one of the following is the correct combination of the current through and potential difference applied across the bulb? So here we're looking for the current through, as well as the potential differences across the bulb. So now what we are supposed to do here is to work out the formula that is actually going to show us how we calculate our current, right? So I will start with the data or the information that is actually given there. So this is our data. According to the information there, we have got our charge there, our charge, or Q, or just a capital letter Q there, is equivalent to 3 coulombs, like that. Then we also have our resistance. I'll just say resistance here, resistance, which is equivalent to 6 ohms. Then the third variable given there is our time. I'll say delta time, which is equivalent to 12 seconds. Okay, so this is the information that we are actually given. And then according to the formulas that we have, we know that we can calculate current like this. Current is equivalent to charge all over change in time. Therefore, let's work this one out. So this means that we are going to have our current is equivalent to our charge. We said is 3, so it's going to be 3 all over the time that is taken there is given as 12 seconds. So if we are to punch this in our calculators, 3 divided by 12, we're going to get an answer of 0.25 amps, 0.25 amps, like that. Then the next one is potential difference. How do we actually calculate our potential difference? Remember, potential difference is same as our voltage. So we're going to formulate our triangle there which starts with voltage at the top, then current there, then our resistance. So in this case here, we're asked to calculate the potential difference, which is our voltage. So we're going to say voltage is equivalent to current multiplied by the resistance. So having this now, our current, according to our calculations, we got a current of 0.25 amps. Therefore, we're supposed to multiply this 0.25 amps by our resistance. Our resistance in this case is equivalent to 0.25 multiplied by the resistance. In this case, our resistance there is same as 6 ohms, because we're given 6 ohms there. Okay, so if we do our math there, 0.25 multiplied by 6, we're going to get a total of 1,5 volts, like that. So these are our answers there. So according to the information that is actually provided, multiple choice there, we can see our current says 0.25 and then our potential difference is 1,5. So it means the correct answer is A. The rest of the other options are wrong. Then we proceed to the next question. Question 1.4. Okay, so electric circuits there. It says consider the circuit diagram below consisting of two resistors in parallel, right? So it says two resistors in parallel there. So we know it's a parallel circuit. Then it continues to say the effective resistance of the circuit is 1.2 ohms, right? So take note, by the term effective resistance, they refer to the total resistance of the circuit. Then they're saying which one of the following correctly represents the resistance of unknown resistor Rx, right? So we know we have two formulas here when it comes to resistors in parallel. So on our data sheet, we'll find this one, 1 over Rp is equivalent to 1 over R1 plus 1 over R2, then depending on how many resistors we actually have. And then the second option is where we are going to say product over sum. Product all over the sum, right? So for this option, the second option here for product over sum, please do take note that this one here is only applicable when we're having two resistors in parallel, and again, it's not there on your data sheet. The one that you're actually going to find on your data sheet is the first option, but however, I will actually opt for the second option for now to work out this information. Okay, so according to this, if we're to start with our product over sum over there, we're going to say the top resistor is 2 ohms, and then the other one at the bottom is Rx, and then these are supposed to give us a total of 1,2 ohms. Therefore, I'm going to say 2 multiplied by Rx, which is the product at the top, all over the sum, which is same as 2 plus our Rx. And then we're given that this should be equivalent to 1,2, right? So if we were to do our math there, from the top part there, it means we're going to have 2 Rx all over 2 plus Rx, which is equivalent to 1,2, right? So multiplying with the base, which is 2 plus Rx on both sides, we're going to have a 2Rx is equivalent to 1,2, and then everything in brackets there, 2 plus Rx, like that, right? So if we're to expand our bracket there, we're going to have something like 2Rx is equivalent to, if we multiply 1,2 by 2, we're going to get a value of 2,4, which is 2,4, then plus on the other end 1,2 Rx, 1,2 Rx, like that. Okay, so now in this case here, we're having 2,4 as well as 1,2. So let's group the like terms there. It means 2Rx minus, since we're transposing 1.2 minus 1,2 Rx is equivalent to 2,4. Then we add okay, plus 2,4. Then at the end of the day, this is what we are having on our right hand side, only 2,4 there, 2,4. Then after this, now let's actually solve the math there. It means if we subtract 2Rx minus 1,2, we are going to get a total of 0,8 Rx. So 0,8 Rx is equivalent to 2, 4. After that, we are supposed to make our Rx the subject to the formula. It means we are supposed to divide both sides by 0,8 all over 0,8. So if we do our math there, that side on the left cancels, then we are going to get a total value of 3 ohms. So our Rx is going to be 3 ohms. So if we were to look at our answers there, it means our correct option is option D, which is 3 ohms. Then we proceed to the next question, which is more of chemistry. It reads salt crystals such as sodium chloride. So we're having our crystals in terms of sodium chloride hold together so well because the anions are strongly attracted to. Okay, so in this case here, we're going to start with the anions, right? So it means here we're having our anions, the anions. It means here the N, take note, just like for you to easily remember, just consider your N there to represent the negative part, right? Negative. So remember, the anions are negatively charged. Then if we were to look at the cations, CAT, the T there is actually going to represent our positive, right? So I'm going to say it's a T there, which represents our positive. So T there for positive, right? So we now know our cations are positively charged. So in this case, we know unlike charges attract. So unlike charges attract. Okay, so unlike charges attract, what does that mean? It means a positive and a negative, they actually attract, or opposite charges attract. So it means here, if they're saying the crystals such as sodium chloride hold together so well because the anions are strongly attracted to, yes, you got that one correct, they are attracted to cations because these two are oppositely charged. Okay, so let's look at our answers there. It says protons in the neighboring nucleus, which is wrong. Then B says free electrons in the crystals, which is wrong. Then the neighboring anions, remember, if they were the same anions versus anions, they actually repel because they are like charges. Like charges repel, then unlike charges are the ones that actually attract. So the final answer there is neighboring cations, right? So the correct answer is going to be our option D. Then we proceed to question 1.6. It says which Lewis dot diagram represents an X atom with the highest electronegativity. Okay, so which Lewis dot diagram represents an atom X with the highest electronegativity? Okay, for this question, we are going to refer to our periodic table to see our electronegativity values. Okay, so now let's look at our periodic table. Okay, so there is no need for you to claim it again. So you can see here we're given the values for electronegativity. It shows here. So for example, here is an example, we're given copper and it has an electronegativity of 1,9. Okay, so generally I want you to look at the trends of electronegativity, right? So you will see that the electronegativity, it increases across a period, right? So electronegativity increases across a period. So it increases across a period. So what do we mean by period? Is from left going to the right there. And it also decreases as you go down the group, right? So this is 2.1, this is 1.0, then 0.9. So it means here is also what? Decreases electronegativity, decreases down a group. Like that. Okay, so this is what we're having. So if you're moving from your left going to the right, your electronegativity increases right across the period, but it decreases down a group. Okay, so according to this here, we're having X with a dot there, right? So this dot represents our valence electrons, or electrons that are actually found on the outer shell. So in this case here, if we're only having a dot there, it means this is our X. In this case, this is the X with the dot there. Then let's try and locate another one. So here, B, option B, it means it has got 4 on the outer shell, right? So we're actually going to go to group number 4. So it's 1, 2, 3, and 4. So it means here, this is where we're having our X with 4 valence electrons or 4 electrons on the outer shell. This is our option B. Remember, also the group number relates to the valence or the number of electrons on the outer shell. Then we've got our option C. If we are to count, they were having 2, 4, 6, 7, 7. So it means 7 on the outer shell. So it should be in group number 7. So they gave a symbol of what there? Still an X again. So we're using an X. So this is group number 7. So group number 7, 1, 2, 3, 4, 5, 6, and the last one becomes 7 there. Then they've got our group 8 there, which has got a stable octet, which is our option D. And then this is group number 8. This is going to be in group number 8, like that. So 2, 4, 6, 8, like that, right? So we now know this is our option A, this is our option B, and then this is C, and then the last option is going to be option D. Okay, so according to this here, they're saying which Lewis dot diagram represents an atom X with the highest electronegativity. Okay, so now we know electronegativity increases across a period, right? So it means here in this case, what are we having here in terms of group number 7? We're having an electronegativity of 4.0. Can you see the other option is 2.5, and then the other option is going to be 1.0. So the correct option there is going to be option C, which gives us an electronegativity of 4.0. So our question number 6, correct answer there is option C. Is option C. Okay, then we proceed to question 1.7, which reads 1 mole of any substance 1 mole of any substance contains, right? Okay, so this is refers to the mole concept generally. So generally the correct answer there should be B, which reads 6.02 times 10 to the power 23 particles, right? Those particles can represent our ions and stuff. Okay, so that's the correct answer there, 6.02 times 10 exponent 23 particles, and the correct answer is B there. Okay, so then we move on to 1.8, which is our off-bar diagram, which reads the off-bar diagram for an element is given below, right? So we're given the off-bar diagram there. Then now the number of valence electrons for the above element is, so we're trying to find the number of electrons found on the outer shell, right? So if we are to count here, we're having an S2 here. It means here is an S2 again. This is 2p6, this is 3s2, then this is 3p3, right? So if we are to add the our electrons, is going to be 3 plus 2, which is 5, plus 6, which is 11, 12, 13, 14, 15. So it means here we're having a total of 15, 2, 4, 10, 11, 12, 13, 14, 15 electrons, right? So in this case now, we're trying to find the valence electrons, the number of electrons that are found on the outer shell, okay? So generally, if we were to draw our shells there, we know the first shell is going to accommodate a maximum number of 2 electrons. So it's going to be the first electron and then the second electron. Then after that, we know we're going to proceed to the next shell or next energy level. So in this next energy level now, we're going to like count a total of 8. So there again, let's count our number of electrons. So it means here we're going to have 1, 2, 3, 4, 5, 6, 7, 8, right? If we are to count the total now, we are having a total of 10, and then we're supposed to go until 15, right? So this becomes our outer shell there. So we're left with our main electrons on the outer shell. So from our 15 there, our 10, we have actually accommodated 10. It means now we're going to be left with 5 electrons. So 1, 2, 3, 4, 5. Okay, so the main focus now is on the one on the outer shell, right? So the one on the outer shell, these are the number of electrons. So it's 2 plus 1 there, which is 3, plus another one 4, plus another one 5. So our correct answer there is 5. So from our option there, we can see the correct answer should be option D. That's our correct answer there. Option D is the one that is actually correct. Then we proceed to the next question, which reads, the minimum energy required to remove an electron from the outermost orbital of an atom in a gaseous state is dash, right? So this is referred to as the ionization energy, which is the minimum energy required to remove an electron from the outermost orbital of an atom in a gaseous what state, right? So, kinetic energy an object possesses due to this Swiss motion. And then this one, option D, the potential energy energy possessed by an object due to its position above the this surface, right? Then we proceed to the next question, which is 1.10 there, which reads the atomic structure the atomic structure of atoms Q, R, S, and T are shown in the table below. Then they are given the number of protons, number of neutrons, number of electrons. Then it says now the question, which two atoms are isotopes, right? So now the first thing that we are supposed to do there is to define the term isotope, right? So isotopes are atoms of the same element. Let me just define it. Atoms of the same element, having the same number, of protons, but different number, different number of neutrons, like that. Neutrons. Okay, so this is what we're having here. So we know, according to this, what is going to be the same here is the number of what? Number of protons, right? So the number of protons, they must always be the same when it comes to an isotope, right? Then what's different here should be the number of neutrons, right? So different number of neutrons, like that. Okay, so this is what we're having here. So according to this table here, we must focus on the number of neutrons that are actually the same, right? So if we were to look at these options that were given here, the number of protons there, can you see we're having a 6 here, we're also having a 6, right? So according to our definition here, we're saying same number of protons but different number of neutrons. So let's compare the neutron number. You can see again the neutrons are different, so it's 7 here as well as 8 there. So our options according to this is a Q and an S. So a Q and S, we find it to be option A. So our correct answer there is going to be option A. Okay, having said that, we're done with the first session, which is our multiple choice. Now we're heading to the structured question, which is question number 2. It says in our everyday lives, we see mixtures all the time. A mixture of different foods such as meat and vegetables is called a stew. A mixture of water, salt, and other substances can be found in seawater, and a mixture of gases such as carbon dioxide, oxygen, and nitrogen air. So this is a mixture there. Okay, then after that, we're given stew here. And then we're given seawater, and then we're also having our air there. Okay, so now the first question reads, from the examples given, identify a homogeneous mixture. Okay, so according to this, homo means the same. Homo means the same. So a homogeneous mixture is a mixture of uniform composition, right? Homogeneous mixture is a mixture of uniform composition. So by that, we mean that there is no demarcation where you can actually say this part A ends here and then part B ends here by just like looking at them, right? So if we look at our option A that says our stew there, from this, we see there is meat, right? And as well as vegetables. At the end of the day, you can actually identify the meat part and the vegetable part that actually formulates our stew. But then when it comes to seawater is just like water. So it's our H2O there. So we cannot say water, since it's seawater, some say it's salty. Since it's salty, now we can see the salt part and the water part. So our correct answer there should be our water there. Our seawater, Okay, that's the first option. As well, the second option is going to be our air, right? So if you wrote seawater or air, you should be correct. Since we see this thing says a mixture of gases such as carbon dioxide, oxygen, and nitrogen air. By looking through the air, you cannot say I can see carbon dioxide ends here and then oxygen starts from here, then after that nitrogen. Okay, so that's why we're saying this is a type of a homogeneous mixture, a heterogeneous mixture. The mixture is not actually uniform. We can easily identify different parts or composition that actually makes up that heterogeneous mixture. Then it says 2.2 here, right? The formula of the following substances, right? So we're having our water there. Our water, the formula for water is H2O, right? Then our nitrogen 2.2.2 says our nitrogen, right? So our nitrogen is written as N2. Why is it N2? Because this is a diatomic, it's a gas, right? So it says nitrogen A, which is form of a what? Of a gas there. So it's diatomic there. We're going to write our nitrogen, which is N2, right? Then 2.3 reads classify the following substances as pure or impure, right? So now we're having the first option there that says our table salt. Then the second one is our oxygen, right? So our table salt there is going to be our sodium chloride, right? So this is a mixture of like a pure substance is a substance with sort of like the arrangement is actually uniform. For example, sodium chloride, everywhere you go, your sodium chloride will remain as what NaCl, right? So by definition, generally, a pure substance is a substance that cannot be separated into simpler components by physical methods, right? So you cannot separate these into their components by physical method for you to separate sodium and chlorine there, right? Then so it means this one is going to be a pure substance, right? Okay, then our oxygen again is going to be a pure substance. Okay, then the next option, the question reads 2.4, explain your answer in question 2.3.2. In this case, they are asking us to explain why we're saying our oxygen is a pure substance, right? Okay, so oxygen is a pure substance because it cannot be separated. So oxygen, we can say oxygen is a pure substance, because because it cannot be separated into simpler components by physical methods, by a physical method. Okay, so having said that, we're done with question 2.4. Okay, so generally here, explain your answer. They were trying to say, in other terms, they were saying define a pure substance. So it's more of a definition of a pure substance. Then we proceed to question 3. It says matter exists in one of 3 states. Okay, so matter exists in one of 3 states, namely X, Y, and Z. And then matter in state X has a fixed shape. Okay, so something that has got a fixed shape and a fixed volume there, it should be a solid, right? Then it says matter in state Y, it takes on the shape of the container. It takes on the shape of the container that is in, and then matter in Z completely fills the container. Okay, so here it means here the first part, here our X, in this case our X, we can say our X according to the statement refers to a solid. And then our Y represents our matter in state. Matter in state Y takes on the shape of the container that is in. And then it means this one should be our liquid liquid according to the statement, liquid, and then our Z, meta Z, instead Z completely fills the container that it is in. So our Z there is going to be our gas. Okay, so that's it. Then after that it says matter can change between these states by either adding heat or removing heat. This is known as a change of state. Then 3.1 asks us to identify the state of Y. Okay, so we've already alluded above there that is going to be a liquid. So the state of Y is a liquid. Okay. Then after that, we've been asked to define the term boiling point. That's our question 3.2. Okay, so when it comes to the definition of boiling point, it should be written as the temperature. Okay, so if you look at your marking guide, it should start with the term temperature. If you don't start with the term the temperature, then you are wrong. So we're saying the temperature of a liquid liquid at which vapor pressure, at which vapor pressure, at which vapor pressure, vapor pressure equals atmospheric pressure, equals atmospheric pressure, atmospheric pressure. Okay, so this is what we are having as a definition for the term boiling point. So the temperature of a liquid at which its vapor pressure equals atmospheric pressure. Okay, then we proceed to underneath there. It says the graph below represents the heating curve of a substance A that starts below its melting point. Okay, so it starts below its melting point. Okay, so it means here is 30 going downwards there is going to be below our melting point. Okay, so it says according to this, what is the boiling point of this substance? Okay, so we're looking for a specific temperature where this actually what boils. Okay, according to this, if we can just like split this graph into different parts, we'll say here was more of more of a solid. Okay, then here we are having more of a liquid, and then after that it formulates a gas like that. Okay, so take note of these lines here, so where there is more of like motion or movement there, and then also we need to take note of these parts that are actually flat there. Okay, so these flat parts. Okay, so here the temperature is constant. The reason behind why our temperature is constant here is because energy is used, energy that is actually absorbed is used to overcome the intermolecular forces or the bond within the particles, right? Okay, then after that the particles gain kinetic energy, as you can see there. So according to this question, it says what is the boiling point of this substance, right? So here we're having a solid, then liquid. So for it to change to a gas there, it should be at the boiling point. So here it means our boiling point is at what? 90 degrees Celsius. So our boiling point there is 90 degrees Celsius. Okay, then we proceed to the next question, which reads, in what state is this substance in the graph at the following temperatures, right? Okay, so we're given different temperatures and we're supposed to refer to our graph there, right? So we're given a temperature of 45 degrees, right? So I've already indicated there on the graph. So our temperature there, so as you can see, it's actually below 60 and above 30. So this portion here represents our solid, right? So this portion here represents our solid. Therefore it means this substance there at 45 degrees is a solid, like that. Okay, then we say 3.4.2 at 65 degrees. Okay, you can see there at 65 degrees, since already at 60 we are above there, it means there is gain, so there is a change of state there to a liquid. So at 65 degrees there is a liquid, right? Okay, I know you are following through. At 100 degrees is going to be what? Yes, you got that one correct, right? It means at 100 degrees there, which is already above our 90 there. So our boiling point is 90. So if you go beyond 90, it means this formula is a what? A gas. Yes, it is a gas. Okay, then after that, we've been asked for 3.5 to draw a cooling curve of substance B using the information from the table. So table below. So this is our substance B. Then our boiling point there is given as 180 degrees. Then melting point there, I'm not sure what's this mark allocation and stuff, but I will just like draw the graph is from the information that is actually given. Okay, so your x-axis there is going to represent our time. Okay, so our time there, we're going to say time. Then remember here we're going to say in minutes, so I'm just going to say minutes like that. Okay, then go up a little bit there, and then I'm also going to have my temperature there. I'll just say temp in degrees Celsius. Temperature in degrees Celsius. That's the vertical part there. Okay, so it means here this substance there is actually what it says. Their boiling point is 180. So it means they at 180 we are going to have let me just like indicate here with the dots. I'm going to assume this was my 180 degrees. Okay, so this is 180. Okay, so it means here what was happening there, it was already boiling at what, at 180 degrees, right? And then after that, now we're going to drop down like that, a flat line. Then after that it's going to drop. Okay, so it means here draw the cooling curve. So if we're drawing a cooling curve, again we're going to also try and include all these changes in what, in phase like that. Okay, so it means here it was more of what, a gas. Then the second part, it formulates a liquid. Then the other part there is actually going to formulate our solid. So this is a liquid, and then a solid going down like that. Okay, so at the end of the day we're going to have a shape like this, and then maybe here we're going to have a temperature that is heading towards the negative. Towards the negative, I'll just say negative VE there. Okay, so those are the things that they are looking for. So what they will actually mark there is going to be your 180, which is your starting temperature, and then also they will consider the shape of your graph, and then that's another mark. And then the final mark is did you label your x and y axis, which is your temperature in degrees Celsius, and your time in minutes. Then you can get your 3 marks like that. Then we proceed to the next question, which is question number 4. It says consider the following substances given in the table below. So we're given KBr, potassium bromide, then NH3, then Cu, and then HF. So these are the substances that we've been given, right? So the first question they asked us to define a covalent bond. So covalent bond is defined as a type of bond that involves or includes the sharing of electrons between atoms to form molecules, right? So this is the sharing of electrons, sharing of electrons between atoms, to form molecules, Okay, so this is our definition for a covalent bond, right? Okay, so now 4.2 reads from the table given above, write down the formula for the substance that have a covalent bond, right? Okay, so covalent bond, it is the type of bonding where we use our outermost electrons that are found on the outer shell, right? So again, as a hint here, we are actually going to have a non-metal versus a non-metal. So this is a non-metal versus a non-metal. Okay, non-metal. Okay, so in this case here, if you look at the top there, we're going to have our NH3. Both are non-metals, so nitrogen and hydrogen, they are all non-metals. Okay, NH3, and then we also have our HF there, right? So which is our hydrogen, and then our F, our fluorine there. So those two are actually our they're actually going to formulate a covalent bond, right? Okay, so now it says from the table given above, also write the formula for the substance with a metallic bonding, right? So metallic bonding there is going to be our Cu. Okay, so a metallic bond Cu actually formulates a metal bond, right? So someone might ask, how does it formulate a bond, a metal bond, right? So here what we're actually going to have is that these usually are metal atoms in a metal, right? Okay, so they formulate a giant of what atoms are arranged in a regular pattern, and then when metals are together in a metal, they give up what electrons on the outer shell, right? So if I'm to formulate like a drawing there, let's say we've got this part that is referred to as our copper, which is our copper metal, right? So what it means here, within this copper there, we are actually having our protons, or the positive part, as well as our electrons, right? So we're saying when these metals are together in a metal, they give up our electrons on the outer shell, and then they share with the other atoms in the metal. So atoms in become positive ions case, and then the other ones actually, because they actually what lost the electrons on the other end, right? So these atoms are the ones that actually built everything, boiled actually everything together to a regular structure to formulate a metallic bond, right? So as an example here, I'm just having my copper. It means here we're having the positive part, right? So I'm going to say this is the positive part, and then we're having our negative there, our negative there. Okay, let me just like make it bigger so that it can be visible to everyone. Okay, so let's say we're having this huge metal plate, right? Okay, so this is my metal plate there of copper. Therefore it means here I'm having the positive part, right? Okay, so the positives, I'm just going to say a positive there. I'm having another positive there. Then also I'm also going to have another electron there, which is actually what negatively charged, right? So at the end of the day, right? So it means the positives are attracted to the negative, right? So these negatives are found like around there. So that's what we refer to as a sea of delocalized electrons, right? So the positives and the negatives actually attract each other at the end of the day, formulating an electrostatic force of attraction. Then the next question there is 4.2.3, which is an ionic bond, right? So an ionic bond there formulates between a metal and a non-metal. So it's a metal here in this case plus a non-metal. So we're having a metal and a non-metal. Okay, so now if we're having a metal and a non-metal, according to our options there, it means the correct answer should be KBr. So our correct answer there is KBr for question 4.2.3. So just to write it on the side, our correct option there is KBr, like that. Okay, then 4.3 reads give a reason for the answer to question 4.2.3 above. Why we're saying KBr formulates an ionic is an ionic what compound, right? Okay, generally we already said a metal and a non-metal. So what we're saying here in this case is that our K there formulates our metal, right? So K is a metal. Okay, the potassium there is a metal. Then after that Br, you can just say comma, Br is a non-metal. Okay, non-metal, like that. Okay, so then how is an ionic bond formed? So an ionic bond is formed by the transfer of an electron from, so ionic bond is formed by a transfer of electrons from a transfer of electron from potassium to potassium to our bromine, which is our Br. like that. Okay, this is what we are having there. Okay, so that's the correct answer, or the reasoning behind is like that. Okay, then 4.4 there, I'm going to just like split it a bit there for question 4.4. Okay, so our 4.4 reads there, define the term ionic bonding. Okay, so this is a bond that actually involves that involves or a type of bond that involves the transfer of electrons, transfer of electrons. I'll just like write E negative for electrons to form cations. Okay, to form cations. Remember at the top there we spoke about our cations and our anions, right? So it formulates a cation and an anion that attract each other Remember, we said unlike terms or unlike charges attract each other, attract each other to form a formula unit, to form a formula unit. Okay, so that's our definition there of an ionic bond, right? Then 4.5 reads we've been tasked to draw a Lewis dot structure for NH3, right? Okay, so for this one, I'm going to make use of this space there for NH3, right? So we've been asked to write a Lewis structure for NH3, right? So this is our NH3 like that. Okay, so it means now we're supposed to employ our periodic table. It means our nitrogen, let's look at our nitrogen, right? So our nitrogen has got how many electrons? It has got a total of 7, but if we look at the group there, it falls under group number 5, right? So what does that mean? If it's in group number 5, it means it has got 5 electrons on the outer shell, right? Okay, according to this, we're going to say our nitrogen there, we start with 1 electron, 2, 3, 4, and a total of 5. Okay, so according to this here, we have been told that we are having how many hydrogens? 3 of them, right? So I'm going to indicate our hydrogens there. It's going to pair there, our hydrogen there, and then another hydrogen there is going to be attached there, then another hydrogen there, like that, right? This formulates our NH3. So that's the structure, how we're supposed to represent the structure of what? Of NH3. Okay. Also take note of this. We also have what we refer to as our lone pair, right? The pair at the top there is referred to as the lone pair. Okay. So this is the lone pair, and then again here on the other end we are having these ones, right? These ones are referred to as the bonding pair. So we're going to say the other one is the bonding pair. Okay, so we have lone pairs as well as bonding pair. Okay, then back to the question there. We've been also tasked to write to draw a Lewis dot structure for KBr. Okay, back again. So our KBr there, let's try and work out our KBr. So we're having our K and then our BR. Okay, so how do we formulate this one, right? So if we look at KBr, we said it's going to formulate what type of a bond. If you can go up there, we said it's an ionic bond, and then an ionic bond we said is between a metal and a non-metal, and it involves the transfer of electrons, right? So electrons are going to be transferred from the cation to the anion, which is negative, right? Okay, so if we are to refer to the periodic table there, we will see our potassium, our K there, right? So it's in group number 1. Remember, group number 1 can donate how many electrons? 1 electrons. And then we also need to look at our BR there. Okay, so our BR according to this is in group number 7, right? So if it's in group number 7, what does that mean? It means it can accept an electron, so we're going to have a negative 1 there, right? So at the end of the day, if we were to draw this, it's going to look like this. Okay, so originally our potassium was having how many? Just 1, right? Then our BR on this other end, it was having a total of 7 because it's in group number 7. Okay, 1, 2, 3, 4, 5, 6, and a 7. Okay, so for this one to be stable, for our Br to be stable there, it needs or to obtain a stable octet, it needs an electron, right? So it means our K there is going to give out an electron, and so that our Br can be stable. So if K is to give out an electron, this is what is going to happen there. We are going to have a K, then we usually put it in a square bracket there, and then a positive, right? So why is it positive? It's now because it has got more protons than electrons. Then what happens to our Br that actually receives also? What happens to our Br? Let's just like draw there. Our Br is going to be 1, 2, 3, 4, 5, 6, 7, and then I will actually indicate the one that was actually received there, 8, like that. Okay, so this is what we're having. So at the end of the day, if this is what we're having, it means here we're having more electrons than protons, therefore it's going to be a negative. So if you answered it like that, then you are going to get yourself a total of 2 marks. Then we proceed to the next question, which is now on question, we are now on question number 5. Then it says the image below shows an extract of table 3 of the periodic table of elements and focuses on the 3 magnetic elements. Okay, so the image below shows an extract of table 3 of the periodic table and focuses on 3 magnetic elements, right? So the most important part there, it says 3 magnetic. Okay, so the part that I actually wanted there is the part that says magnetic, the magnetic part. Okay, so we proceed there to answer the question. So this is the table, periodic table, a small sample of the periodic table, or just an image. Then here we've been asked to describe, under question 5.1, describe how to test and classify. So we are testing and classify these metal elements as magnetic, right? So for it to be magnetic, it should be attracted to a magnet, right? So what should we use for it to be attracted to a magnet? It means we must actually employ or make use of a magnet. So in this case here, we're going to bring a magnet closer. Okay, so here, what are we going to do? We're going to bring the magnet closer, bring the magnet closer to the metal, okay? So if you bring a magnet closer to a metal, what should actually happen there? Okay, so what we're having there, according to the periodic table, the ones that are circled is Fe. Then we have our CO, which is our cobalt. Then we also have our Ni, which is our nickel there, right? Okay, so if these are attracted, if they are attracted, what does that mean? Yes, it means they are on metals. If they are attracted by the magnet, therefore they are magnetic. Therefore they are magnetic. Okay, magnetic. Okay, so if not, generally, if not, then they are non-magnetic, like that. Okay, then we proceed to the next question that is here, 5.2.1, that says define the term atomic number. Okay, so these are the number of protons. These are the number of protons, number of protons in an atom of an element. Number of protons in an atom, of an element. Okay, that's the definition that we're actually having there for atomic number. The number of protons in an atom of an element. Okay, so then the next question here, we've been tasked to define isotopes. Please do take note of this definition of terms because they are actually worth 2 marks, and 2 marks is actually a lot, right? So for this one, I'm going to define it on the other page there. I'm going to say isotopes, okay? We already defined this one, but I will actually repeat since it's a question. It says atoms of the same element. These are atoms of the same element, atoms of the same element, atoms of the same element, having the same number, the same number, the same number of protons, but different number of neutrons, but different number of neutrons, Okay, so this is what we are having here as a definition for an isotope. Okay, back to the question. It reads 5.3. Natural nickel consists of 5 stable isotopes, right? So we're having a total of 5 stable isotopes as shown in the table below. Then give the term that represents the value 58 in nickel, what? 58. So we're looking for that part there, okay? So we're going to make things easy. We're actually going to go through our periodic table and look for nickel there, right? So this is our nickel, right? So since it formulates our isotopes there, that's why we're having a 59 there, right? So it means this is our Ni there. And then according to this, right, if you are to look at the periodic table there, you are already given, right? As an example, we are given copper, and then we are given this number as the relative atomic mass, right? So it means the number that we are given here is going to be our relative atomic mass, right? Relative atomic mass, okay? So for it to be easy, just refer to your periodic table, which will give you your relative atomic number, mass, and as well as the atomic number. Okay, then 5.3.2, it asks us to calculate the atomic mass of what? Of nickel, right? Okay, so relative atomic mass. Okay, I'll just say AR for relative atomic mass of what? Let me just say Ni in bracket, right? So according to the data that we're having there, we're having our percentage abundance, and then it's 58, then 26, like that, right? So it means here nickel 58 comprises of how many percent? I'm going to multiply that percentage 58 but multiplied by that percentage, which is 68,27. Then put that in brackets, say plus, and then move on to the next one. We're having our 60 there. Okay, so it's Ni 60 multiplied by the percentage there is given as 26.10, which is 26.10, and then add again plus, and then in brackets we've got our nickel 61, which is 61. Take note, it's not a negative, it's just that so that they can indicate it's nickel dash what 68. So it has got a percentage of 1.13. Then we add again, move on to the next one, which is our 62 then, and then its abundance, percentage abundance is 3.59, and then we add again the last one there, which is our 64, then multiplied by the percentage abundance, which is 0.91, right? So as a percentage, right, because this is a percentage, so if they say percent means over 100. Okay, so now let's employ our calculators to work out this one and see what we get. Okay, so if we are doing our math correctly, let me see what I'm getting here. 58 by 68.27 plus 60 plus multiplied by 26.10, then plus 61 times 1.13, and then plus again in bracket 62 times 3.59, then plus 64 times 0.91 all over 100. Okay, so according to my calculations, I'm getting I would say relative atomic mass for nickel is equivalent to, getting a value of what, 58.75. Okay, so this is my final answer there according to my calculations. Okay, then I will proceed to question 5.5, which is where we have been actually tasked to draw the diagram, draw the Aufbau diagram. Okay, Aufbau diagram, orbital box diagram of what, the chlorine atom. Okay, so chlorine atom. Okay, so now we're supposed to go to our periodic table and refer to chlorine, right? Okay, so according to this here, chlorine is in group number 7, and then the atomic number there is 17. Okay, so now I will actually make use of this page of ours. Therefore, I'm going to say Cl there. Cl is 17, and then 35.5, like that. Okay, so I'm going to start with the SP notation there. I will start with the SP notation, right? So we're having 17 there. Okay, according to the SP notation, I will say 1s2, then 2s2, then I'm going to have a 2p6, then actually after that 3s2, then 3p 5, because it's 17, right? Okay, then after that, now I'm just gonna flip this energy level around, right? So I'm going to start with that side, going that side. Okay, so this is what I'm going to have in terms of my Aufbau diagram, right? I'm going to have something like this. Then at the bottom there, I'm going to start with my 1s2, right? So I'm going to say 1s2, like that. Okay, so now how many electrons do we have there? We're going to have a 2, right? Remember, they are formulating opposite spins. Then I'm going to have my 2s2, then after that 2s2. Okay, to make it easy, let's start like top bottom to make it easy. Okay, so I'll just like draw this line going downwards there. Therefore, I'm going to have my 3p5 also, then I'll also have my 3s2, then I was having my 2p6, then I was having my 2s2, then after that I was having my 1s2. Okay, so if it's like this, I think it's going to be easy for everyone. Then opposite spin there for 1s2, and then also opposite spins there for 2s2. Then after that, we're going to step aside to show a change in the what, energy level. Then split this into 3 different parts. Okay, so 1, 2, and 3, right? So remember, you fill 1 first before now coming back to make double. So it's 3 now, then 4, 5, as well as 6, then 3s2. It means we're going to go back again to the S energy level, and then we're having a man of them, 2 of them. After that, the final one is going to be 3p5, right? So this is again there. Try and align them in such a way that the p orbitals align to each other, with each other, as well as the s orbital, they align with each other. So I've occupied 3 there, then they're saying 4, and then 5. Okay, so this is our Aufbau diagram for chlorine. So this is the correct diagram. If you flip it around, start with 1s2 going downwards, you are actually going to be marked wrong there. Okay, then I proceed to the next question. The next question, which is question 6 there, it says 5 grams of zinc granules are added to 400 cubic centimeters of hydrochloric acid. So we're having 5 grams there. Okay, we're having 5 grams there. 5 grams of zinc. Okay, of zinc there are added to 400 cubic centimeters of hydrochloric acid. Okay, that's our HCl. Then to investigate chemical change of the reaction, the change in the mass of the flask containing the zinc and the acid is measured by placing the flask on a reading balance. Then the reading on the balance shows that there is a decrease in mass during the reaction, right? Okay, then we'll proceed to say the reaction takes place the reaction which takes place is given by the following balanced equation. Then we're having our zinc. Let me just scroll a bit up there and see. Okay, yeah, I think I skipped a question. Okay, 5.6, 5.6, 5.6, sorry about that one. 5.6 there, it reads, determine the charge of ion after removing 3 electrons from the ion atom, right? Okay, so our ion there is our Fe. Our ion there is our Fe. Our ion there is our Fe. Then if we were to remove 3 electrons, right? Okay, so if we are to remove 3 electrons, it means at the end of the day it's going to have an extra of 3 protons, right? So it's going to be the Fe3 plus, right? So Fe3 plus, that's our final answer for 5.6. Then I'll go back to question 6. Sorry about that one there. Then we are asked to define 1 mole, right? So we're given an equation. Then after that we've been tasked to define a mole there, right? Okay, so a mole is defined as the amount of substance having the same number of particles. I'll just write it down. The amount of substance, the amount of substance, the amount of substance. This is our amount of substance having the same number, having the same number of particles as there are particles as they are atoms in 12 grams carbon, as they are atoms in 12 grams carbon 12, carbon 12, like that. Okay, that's our definition for 1 mole, right? Okay, then 6.2 reads, calculate the concentration of hydrochloric acid that actually reacts. Okay, so we're looking for concentration of the hydrochloric acid that reacts completely with how many grams? 5 grams of zinc granules there. Okay, so here I'm going to start with the number of moles, right, of zinc, since we're given the mass of what? Of zinc. Okay, so I will make use of our space there. Allow me to erase the off-bar diagram and all real quick. Okay, so they were given 5 grams of zinc, and then we're supposed to calculate the number of moles of the zinc. Then after that we're going to use our mole ratio from our balanced equation, right? Okay, so here I'm going to say let me change color. Okay, so from here I'm going to say the number of moles of zinc, right? Number of moles of zinc are by formula. This is equivalent to m over m, mass over molar mass, right? So therefore here this is equivalent, the mass that we're given there is actually 5, okay, over the molar mass. Now we're going to employ our periodic table to look for zinc, right? Okay, so according to this my zinc is 65 there, 65, right? So the mass for zinc is 65, therefore I'm going to say all over 65, right? Okay, so if I'm to employ my calculator, 5 divided by 65, I'm getting a value of 7,69. Okay, 69 times 10 exponent 2, okay, negative 2 moles. Okay, mols or moles, they're still correct. They're all correct. That's the first step there, right? Okay, then now I'm going to like say the mole ratio, make use of the mole ratio or mole ratio there. Okay, so I'm going to compare my zinc versus my hydrochloric acid, right? So the one that I've been tasked to calculate there, right? Okay, so I'm going to look at the mole ratio there, right? So if you look at zinc here, it's same as we're having only one zinc. On this other end here, we're having two. So our mole ratio according to this is going to be 1:2, right? Okay. So the mole ratio, the moles that we actually calculated for zinc here is 7,69, 7,69 times 10 exponent negative 2, right? Therefore, on the other end, we're having 2. It means we have to multiply 7,69 times 10 exponent negative 2 by 2, right? So if I'm to do my math there, I'm getting a value of 1,538. 1,538 times 10 negative 1. Okay, so if I'm to round it off, I'm going to get 1,54 times 10 exponent of negative 1. Okay, so that's my mole ratio. Then after that, now I'm going to say generally this is was my first stage. I will actually indicate using black there. This is stage number 1, then I'm having stage number 2, right? And then let's have the next stage there. Allow me to split my page in like that. Then I'm going to say stage number 3 there, where I'm actually going to calculate my concentration for HCl, right? So it means here I'm going to say concentration for HCl is equivalent to number of moles over the volume, right? Okay, so the number of moles that I actually calculated there is 1,54 times 10 exponent of negative 1 and then all over the volume, right? Okay, so let's go back to our question there. Our volume, I think we're given our volume. Yes, it says 400 there cubic centimeters, right? So we are supposed to convert this 400 cubic centimeters into our dm cubed, right? So how do you do that, right? So 400 cubic centimeters to dm cubed, right? Okay, so for you to get the answer there, you're supposed to say 400 divided by 1,000, right? Okay, so I don't know what you get there. Let me just like quickly work it out. So it means here 400 divided by 1,000, it gives me a value of just a moment, 400 divided by 1,000, 400 divided by 1,000. Okay, I get a value of 0,4, right? So it's same as 0,4, right? So if we're to do our math there, after that, I'm going to get a concentration of 1.54 times 10 exponent negative 1 over 0,4. Okay, this is the answer that I'm getting there. I'm getting a value of 0,38, 0,38, and then I'm going to say the units of measurement is mole per dm cubed, right? Okay, so this pair means over, so we divided the number of moles by the volume, which is in dm cubed, right? This pair, this negative there, shows that it was over there. Okay, so then we're done with our question there. So that's the concentration they've been looking for. Okay, then we proceed to the next question that actually reads calculate the volume of the gas, right? So we're looking for the volume of the gas that is formed if the investigation is performed at STP. Okay, so I'm going to make use of this one. So let's look at the gas there that they are looking for, right? So it means our gas there is our hydrogen gas, which is our H2, right? Okay, again here I'm going to start with what I was given. So the number of moles there of zinc, right? Okay, zinc there versus the number of moles of hydrogen, right? The number of moles of my hydrogen gas, like that. Okay, so according to this, I already calculated from the previous question my number of moles of zinc. There were 7,69 times 10 exponent negative 2. So I'm going to have my 7,69 times 10 exponent of negative 2, like that moles, right? And then it means here, what am I going to have, right? Before I can proceed, I need to just like look at this one. So look at our zinc there. me use a different color so that you can easily identify. Okay, let's look at our zinc there. We said zinc is more of like having how many moles? 1 mole, right? So again here, our hydrogen is more of it like having 1 mole. So the mole ratio according to this here should be 1:1, right? So what does that mean if it's 1:1? If we're using 7.69 times 10 exponent negative 2 moles for zinc, it means we're going to use the same number of moles for actually our hydrogen gas, right? So now we're having our number of moles for hydrogen. Then after that, now we're going to say, since we've been asked the volume of the gas, right? So number of moles is equivalent to V all over Vm, right? Okay, so the number of moles that we're given here is 7,69 times 10 negative 2 is equivalent to the volume. So we've been asked to calculate that volume all over. Then here I'm going to refer to the data sheet, though I'm not going to open it. So it means our STP there, right? Okay, so our STP, standard temperature and pressure, our volume there, molar gas volume is going to be 22,4, or to just like quickly refer to it so that you can see what we are talking about. Let's look at our Vm there. Are we given our Vm? Okay, so yes, so this is the molar gas volume at STP, standard temperature and pressure, and then this is our Vm, and it actually gives us a value of 22,4. Right, this is what we're looking for there. Then we go back to our question there and finish. We're almost done. We finish it on a high note. Okay, so if we're to do our math there, so it means here V is equivalent to, we just cross multiply 22,4 multiplied by 7.69 times 10 negative 2, and then we're going to get a value of 1,72 dm cubed, because this is the volume. Okay, that's how we go about when calculating question 6.2.2. Then we proceed to 6.2.3, where we asked to calculate the maximum decrease in the mass of the flask, right? Okay, so and here we need to calculate the number of moles, not the number of moles, but the mass of the hydrogen gas, right? So by formula, number of moles is equivalent to mass over a molar mass, like that. Okay, so I already have the number of moles for hydrogen gas, which is 7.69 times 10 negative 2 is equivalent to m, right, all over. Then here we're going to say 2. Why are we saying 2? Because this hydrogen is two diatomics, right? For us to calculate the molar mass for hydrogen, we're going to say m for hydrogen there is equivalent to, hydrogen has got a mass of 1, right, multiplied by 2 of them. There at the end of the day, we're going to get a value of 2. So if we cross multiply there, we're going to get a value of what? Our m is equivalent to 0.15, and then our grams of H2. So this is the mass that actually what escaped the flask. So I can just say escaped. Okay, then I proceed to the next one, which is my question 7, right? Okay, so question 7, there is now my physics, which is electric circuits, right? Okay, so it says in the circuit diagram below, the reading on the voltmeter V1 is 12 volts, and the reading on the ammeter A1 is 2 amps, right? So we're given the reading of the voltmeter, which is our voltage, and then our current, which is 2 amps, right? So then that's the type of circuit that we're actually given. From my point of view here, I think this is a combined circuit, right? Okay, so we're having a combined circuit. It means this other part, 6 and 3, they're actually parallel, but if you are to join them together, they are going to be in series with the 4 ohms resistor. Okay, so the first part there, we've been required to define the term resistance, right? So this is just the ratio. It's a ratio of potential difference, which is our voltage ratio of potential difference voltage potential difference to current, to current, current, like that. Okay, then now question 7.2.1 asks us to calculate the total resistance of the circuit, right? Okay, for us to calculate the total resistance of the circuit, we must actually take note of these two that are actually in parallel. So we'll cut the long story short and make use of the product over sum, since we're only having two of them in parallel, right? So take note, this formula is not there on the data sheet, and also it only applies to two resistors in parallel, right? So I'm going to say 6 times 3 all over 6 plus 3, right? So if I do my math right there, it means at the top there I'm going to get a value of 18, at the bottom there I'm going to get a value of 9. So if I divide this one, what am I getting? I'm going to get a value of 2 ohms, right? Then after that, now it means now I've combined these two. I have combined these two and they're giving me a value of what? Of 2 ohms there, right? So now I'm going to say resistors in series plus resistors in parallel, okay? Let me just say RT, which is total resistance, is equivalent to resistors in series plus resistors in parallel, right? So in series there, therefore, I'm going to have a 4 plus a 2, which will give me a total of 6 ohms. So this total resistance is equivalent to 6 ohms. Take note also, at times they can actually change the resistance. Instead of saying total resistance, they can say the equivalent what resistance. So it just refers to the same as what the total resistance. Then here 7.2.2 says amount of charge. Calculate the amount of charge that flows through the ammeter A1 in 60 seconds, right? Okay, so remember what we're having here is the current, right? So remember, current is equivalent to charge over time, right? Charge over time. Okay, so we just need to make our charge the subject of the formula. It means here charge is equivalent to current times change in time. Okay, so according to the information there, we're given a current of 2 amps there. This is our 2 amps there, right? So we're having a total current of 2 amps. So it means here we're going to multiply 2 multiplied by 60 seconds, which is our time. So there is no need to convert, since our units of time is always in what? In seconds. So I think here I'm going to get a total of 120 coulombs. Then actually now I move on to question 7.3, which reads the 3 ohms is resistor is removed from the circuit, right? Okay, so we're having this 3 ohm resistor being eliminated, right? Then they're saying, how will this charge affect the current through A1? Current through A1, where is my A1 ammeter A1, or at the top there, right? So at the top there we're having a value of how many 2 amps. Now, how is it actually going to be affected there, right? Okay, so write down increase, decrease, or remain the same, right? Give a reason for your answer. Okay, quickly, I'll just like do the math behind this one, but the answer there is going to decrease, right? Okay, so mathematically, just to prove it, we're going to make use of this. So we're having a total resistance of 6 ohms for these resistors when we're having parallel and what series, a combined circuit there, right? But if we were to eliminate this, it means we're having only resistors in series, and then this is equivalent to R1 plus R2. So in this case here, it means we're going to say 6 plus 4, which is equivalent to 10 ohms, right? So it means here we're having a greater resistance. If there is a greater resistance, it means now there is less current that is actually going to flow. So generally we can say the reason behind is because the total resistance increases. So total resistance increases. Total resistance increases in series, and then the total current decreases. Total resistance increases in series. Therefore, what happens to our current? Therefore, current decreases. Current decreases, like that. Okay. Then we proceed to the next question, which is our question number 8 there, right? So here on question number 8, we've been tasked with a group of learners that actually carried an investigation to determine the relationship between current and the number of cells added in series, right? So here it says each cell carries a voltage of 1.5 volts. So we're having a 1.5 volts. Then the diagram below shows the circuit diagram the learners used. Okay, so that's what we're having. That's the circuit diagram there. So as you can see, these are our resistors. They are actually in what? In series, because there's one pipe for current to flow. Okay, so give a suitable investigation for this investigation. Okay, so then we are supposed to identify the independent variable and the dependent variable. Okay, so from the graph here, this is what we are having, right? For you to easily identify the independent and the dependent variable, you're going to make use of something like this. Okay, so it means this one formulates more of a D. So whatever is on your y-axis is your dependent variable, and then whatever is at the bottom there becomes your what? Your independent variable. Okay, so my suitable investigative question is going to be like, what is the relationship between current and voltage? Okay, so I'm going to say, what is the relationship between voltage, between current and voltage, and voltage, current and voltage, for cells connected in series, for cells connected in series. Okay, so that's my investigative question there. Okay, so take note, your investigative question shouldn't be a closed question where you can answer it with a yes or a no. Again, you should also be able to include both the independent and the dependent variables, right? Okay, so you can see we're having current there as well as what the voltage there. Okay, so that's how you actually supposed to go about it. Okay, so then the next question they were tasked to answer is to define the term EMF, right? Okay, so EMF is defined as the work done per unit charge, work done per unit charge, per unit charge by the battery, by the battery, and then you can get your 2 marks. And then the question says identify the following variables. Independent variable, right? Okay, so your independent variable there is going to be your voltage, right? Okay, so the number of cells actually affect your voltage there. Okay, so your independent variable there is going to be your voltage, and then the dependent variable is going to be your current. Okay, so this is your current. Okay, so if I can go back to the graph here, when I said this formulates more of a D, right? So this is the dependent variable, and what are we having there? We are having your current, right? And then the number of cells have to do with your voltage or your potential difference there. They formulate your independent variable because they fall at the bottom. They're formulating more of an I there. Okay, then we proceed to the next question, which is our 8.4. It says predict what will happen to the brightness of the light bulb as more cells are added into the circuit. Okay, so it will increase. The brightness increases. It will increase since voltage is also directly proportional to current. Increase since voltage is directly proportional to current. Okay, then the 8.5 says use the information on the graph to calculate the total voltage of the circuit at 30 amps, right? So what we're looking for there is to calculate the total voltage at 30 amps, right? Okay, so we're having a 30 amps there, 25, 25, 25, 25, 30. And then here, what are we having here? We're having a value of how many? 10, right? So it means we're having a 10 there. And then at the end of the day, what does that mean there? It means we're having a 25 and a 10. Then other information we have are 1.5, right? So each cell it is equivalent to 1.5 there, right? So if we're having 1.5 volt cell and then we're having a total number of cells of of 10, right? So now we've been tasked to calculate the uh the total voltage, right? So it means here we're having 1.5 cell for 1.5 volts each cell, and then a total of how many of them of 10, right? So if we multiply this 1.5 by 10, we're going to get a total of 15 volts. Then we get our 2 marks there. Then it says 8.6. An ammeter was connected in the circuit and gave a reading of 24 amps in 2 minutes. And then calculate the energy dissipated by the circuit. Calculate the energy dissipated by the circuit. Okay, so I'm going to try and manipulate the space at the bottom there. So it means our charge there, we know how to calculate our charge there. Our charge is equivalent to current multiplied by change in time. So in this case here, what am I having? I'm having a current of what? 24 amps, right? So that's my 24. Then I'm supposed to multiply with time, right? So we're given time in minutes. So I have to convert this one to seconds, right? So we know every minute is made out of what? 60 seconds, then multiplied by 2. So I'm going to get a total of how many seconds? 120 seconds, like that. Okay, so it means this time here I'm going to make use of it, and then 24 multiplied by 120, and then according to my calculator there, 24 by 120, I'm getting a value of okay, it's 2880. Then coulombs. Remember, your charge should be in coulombs, like that. Okay, then after that, now we are supposed to calculate the energy, right? Okay, so energy is same as if we are to look at our data sheet, you'll find out that we have got a formula like this: W all over Q, where your Q is your charge, right? So now, do we have our voltage? Yes, our voltage is 9. Therefore, it means here we're going to say 9, 9, 9, 9, 9, 9, 9, 9. Okay. Okay, then after that, you're going to take your W and make it the subject of the formula. So this is equivalent to W. Then here we are having R at 2880, then multiplied by the voltage. Then at the end of the day, if you multiply, you are supposed to get a value of 25, 920. It shows like that. And then the last question there, it says write down the conclusion for this investigation, right? So okay, so we know as more cells are added in series, the total voltage of the circuit increases. So if we add more cells in series, the total current increases. That's increasing the total current. So as more cells are added in series, the total voltage of the circuit increases. That's increasing the total current. Okay. With that being said, we are at the end of our paper. Thank you. Mm-hmm.